Okay, good morning, everyone. Today I will show you the evolution of the research work I've been carrying through with my research group, entitled Examples of Machine Learning Algorithms to Support the Fatigue Design of Additively Manufactured Metallic Parts. Here we can see a brief overview of what we are going to see inside the presentation, and we can start with the introduction to the problem. So, as we all know, fatigue testing starts with the selection of the alloy, the metallic powders, and then the inputting of the process parameters inside the machine. We can then produce the specimens, and then we can perform thermal or surface treatments to perform finally fatigue testing. But as we all know, this is quite time-consuming and expensive, so this justifies the employment of machine learning algorithms, which are also declined in a probabilistic framework. In order to do so, we need to build a training database to train a neural network, and then this allows us to predict the fatigue life and design against fatigue failures. This allows us to have an idea of the component life before production, and at the same time to save time and money. To do so, we need to scavenge the literature in search of fatigue tests. And while we are doing so, we need to note the process parameters, the risk volume, the thermal treatments, the surface treatments, and the stress amplitude, which are then fed as input to a neural network, which could also be a probabilistic one, as I will show you later. And once the network is trained, we can produce prediction about the PSN curves with the machine learning model uncertainty. And we can also forecast the influence of the process parameter on the fatigue life. To do so, we, of course, need to build a training database from fatigue literature data. In this research, 3 alloys have been exploited for a grand total of more or less 2,500 points. In total, we have a bit more than 70 articles, more than 200 data sets, and as I said before, a bit less than 2,500 points, and we can see them all scattered around the SN diagram. And as an example, I will take stainless steel. So as we can see, the training database for stainless steel is made of 2 columns, which are for indexing. Then we note the process parameters, which are a must. If one of these is missing, the article is discarded. Then we note the risk volume to distinguish between the different testing conditions. And then we note the thermal treatments, which are noted as a Boolean value to denote if annealing or hot isostatic pressing is performed. And then we also note the treatment details such as time, temperature, and pressure. And then the surface treatments are all noted as a Boolean value. The most common one are machining, polishing, grinding, shock peening, sandblasting. And the number of these treatments depend on the alloy, of course. And finally, we have the stress amplitude, which is not reported here, not to clutter the database with more than 100 rows. We can then see the employed fatigue model. So as I've shown before, most of the points lie in the 10 to the third, 10 to the 7 range. So we can reliably model only the high-cycle fatigue regimen. And to do so, we employ a linear model without a fatigue limit, which has 3 parameters. And of course, we could also model the very high-cycle fatigue regimen, but this depends on the available data. And as you can see, we have most of the point lying in the 10 to the third, 10 to the 7 range. And the phenomenon is modeled, of course, assuming a normal distribution that is centered on the mean line, which is the R50 line, that is calculated by minimizing the negative log likelihood on experimental failures and runouts according to these expressions here. The R50 line, of course, as I said before, depends on 3 parameters: the slope, the intercept, and the standard deviation. To increase safety against fatigue failures, we can, of course, also employ the R90-C90 curve, which is having the same slope of the R50 curve, but a lower intercept that is calculated with the Owen method, in which we need to calculate the K-Owen coefficient and exploit the dataset standard deviation. The network can be trained to predict both the R50 and R90-C90 line, but for the R90-C90 life, the training data must be shifted accordingly on this line. So it means that we are having the same stress amplitude, but a smaller fatigue life. And this favors an increased safety and trustworthiness, but we can also employ different level of reliability and confidence depending on the industrial application. The next thing we can see is a brief digression on neural network. So as we all know, a neural network is a black box with input features and output labels. But in reality, the black box is made of hidden layers defined by the number of neurons, which have randomly initialized weights and biases. The training process consists in updating the weights and biases to reduce the prediction error. And the loss could be, of course, either a mean square error, so in case of a feed-forward neural network, or a custom loss function representing an actual physical law. So we are representing a physics-informed neural network. But both of these networks are deterministic, so it means that once they are trained, they give always a constant prediction. Pictorially, the prediction could be this black line predicting the R90C90 line. Instead, if we employ a Bayesian neural network, we can have a variable prediction that belongs to a distribution. So the typical situation could be this one. This happens thanks to variational layers, which employ Bayesian statistic as a part of the machine learning model. And so we can see that, for example, each weight and bias of a variational layer is a random variable instead of a single value. And so the connection between a variational layer and its previous one are modeled by a distribution that we can choose, which could be, for example, as in this case, a multivariate normal distribution with a standardized prior updated to a fully populated posterior during training. So we pictorially pass from this to this for this case. A variational layer, we can see, is defined in the same way as a normal layer. So we have the number of neurons and the activation function, but as I said before, we need to specify also the prior, which in this case is standardized normal distribution, so a null mean vector and identity covariance matrix, and is updated to a fully populated posterior. Another note goes on generalization. As we can see, the Bayesian neural network with the same training data, as opposed to the other one, yields a better generalization. So we can see that the training error is superimposing well to the testing error. And this is not always the case for a physics-informed neural network, or let alone a feed-forward one. Another thing that we have to consider is that with the Bayesian neural network, we are modeling the machine learning model uncertainty, because we can have an envelope of curves belonging to a distribution. And on the other end, if we are predicting the R90C90 life, we are modeling the epistemic and aleatoric uncertainty that is inherent to fatigue. So in this case, we can separate these two contributions by employing this framework that exploits both the R90C90 life and the machine learning model uncertainty thanks to the Bayesian neural network. We can now see some results. We can start with a free prediction at a more preliminary and primitive stage of the research, both with a feed-forward neural network and with a physics-informed neural network. In the first case, we can see that the predictions are almost precise, but the behavior is not so representative of fatigue, is not exploitable in industrial application. In order to try to solve this issue, we can employ a physics-informed neural network to try to encourage negative derivatives, and so having a slope that is representative of fatigue. On the other hand, we could employ a proper statistical formulation for fatigue curves, both by leveraging a feed-forward neural network, and I don't know why the envelope here is not represented well, and we also can employ a physics-informed neural network. As we can see here, for the feed-forward neural network, the prediction is not so good. On the other hand, for the physics-informed neural network, if we are employing as a loss function the negative log likelihood of the entire dataset points, we can see that the prediction improves. But we can see that this is a purely deterministic problem, so it means that we always have the constant prediction. In order to solve this issue, as I shown before, we can employ a proper statistical formulation, so the R90C90 life, and we can use a probabilistic framework that allows us to have a distribution of curves thanks to the Bayesian neural network. This allows us to have enhanced precision and trustworthiness, and at the same time, a better model generalization, as I said before. And as I said before, this formulation allows us to capture the machine learning model uncertainty and to separate this contribution from the epistemic and aleatoric uncertainty of fatigue. So from the set of curves belonging to the distribution of the R90C90 life, that is represented here in light blue, we can select the 10th sample. So it means that we can select the C90 of the R90 C90 life, which is in orange here. And this means that we can be even more safe, because not only we say, okay, this is our prediction, but we can say, this is how much you should trust the prediction. Another thing that we can see is the process parameter influence. This has been done for stainless steel again. So the Bayesian neural network can produce continuous prediction on the life to study the influence of the process parameter. And this has been done for 2 stress amplitude levels, so 200 and 350 megapascals. This is where more data are lying. And the study parameter is varied along its training range, but even outside. And the other input features are all kept constant and equal to the most recurrent values, so as to reduce that uncertainty effect. And here we can see some results that I will discuss now. As you can see, we are using a probabilistic framework because we have a distribution for the predicted parameters. And we can see that for the building orientation, horizontal specimens have a better life as opposed to vertical ones, while for the power, the hatch distance, and the layer thickness, we have that low value influence positively the life, and for the laser scan speed, we have that the contrary holds, so a higher value yields a better fatigue life. As you can see, I have reported some references here. This is done to exploit the fact that the Bayesian neural network predictions are in agreement with the process parameter influence experimental evidence. And we can also see here that we have some vertical black lines. This is to indicate the training range of the database. When the prediction is forecasted outside the training range of the process parameter, we can see that the prediction bands get bigger, and this is quite expected because we don't have data here. Another thing that can be done that is not discussed here is that we can analyze the synergistic influence of more process parameters at once. The last thing that we can see is transfer learning, which is something that is very useful to produce a reliable prediction when a low amount of data is available for an alloy. So let's say we have alloy A, and we have a few training points. To save on fatigue testing, sparse literature data are leveraged. So let's say we have other alloys, alloy B and C. We can leverage these data points belonging to these alloys to improve the precision of the alloy A. And this is done by leveraging multi-material knowledge transfer with the 3 alloys I've shown before. To perform transfer learning, we need to first take a model. So let's say we want to perform transfer learning on alloy A. We take alloy B and C, so the data that we have available. We train a neural network. This neural network is loaded. Then we freeze the intermediate layers. And then we continue training with alloy A, the alloy for which we have few data, for a smaller amount of epochs. Then we unfreeze everything, and we perform some fine-tuning for a even smaller amount of epochs. To corroborate the effectiveness of a transfer learning application for material A, we select an external dataset X that is never seen by the training database of material A. And we create a small training database with these datasets that amount to a grand total of more or less 50 points. We then copy and paste these datasets, and we increase by 50 more points belonging to the same datasets. Then we do the same to reach 150 and 200 points. And this is done for 1 combination, and is repeated up until 10 combinations. So in total, we have 40 small training database of progressive numerosity, so 50, 100, 150, and 200. And then we perform 40 trainings without transfer learning and 40 trainings with transfer learning. So for each validation dataset X of a material A, we can see that we produce an evaluation with the Bayesian neural network for these 80 trainings, and we evaluate both the R50 and R90 C90 life, and we produce PSN curves with and without transfer learning. And the next thing that we do is that we calculate a normalized R2 coefficient calculation. For normalized, I mean we calculate the R2 coefficient on the Bayesian neural network prediction, and we divide by the experimental one. And this is done and averaged over these 10 combinations. And at the same time, this is repeated for the 4 numerosities, so 50 up to 200, and with and without transfer learning for the R50 and R90 C90 life. A small remark, the external validation dataset is always external, and contains 15 points. The fact that it's external means that the Bayesian neural network never sees this validation dataset, so this validation is quite severe. And on the normalized R2 curve, the transfer learning case should be always above the case without transfer learning. So we can see, as the last slide, we can see here the PSN curves for the increasing numerosity, so 50, 100, 150, and 200 points. In black, we have the R50 and R90 C90 life, and in colored, we have the R50 and R90 C90 life with and without transfer learning. And here we can see the normalized R2 coefficient plots. The one dashed is the case with transfer learning, and the undashed one, the solid one, is the case without transfer learning. As an example, transfer learning here has been performed on aluminum. So as the training database, as the previous network, we are selecting a network that is trained on the stainless steel and titanium. And the curves are averaged over the 10 combinations. We can see that transfer learning allows to improve the quality of the prediction because the R2 normalized score with transfer learning is always above the case without transfer learning. And as we can see, but this is quite expected, increases the number of training points score. But most importantly, the transfer learning case is particularly effective when we have a low amount of training data points. And this is what we want to achieve because already 50 points, experimental points, are quite a lot in some cases. And so, the conclusion of this research are that machine learning allows to save time and economical resources when it comes to predict the fatigue life of additively manufactured specimens. This is possible by leveraging numerous literature datasets for the most common alloys, titanium, aluminum, and stainless steel. And we can see that the Bayesian neural network allows to give prediction with a machine learning confidence level for improved safety. And at the same time, we can see that it's possible to study the influence of the life for each process parameter. And transfer learning allows to improve the prediction quality when the training data is low by leveraging the data of other alloys. Here we can see the references, and that's all. Thank you for the attention. If you have questions, I have open to answer them all.